This problem is going to involve an existence and uniqueness proof. Let U be any set. Prove that there's a unique A in the power set of U, such that for every B in the power set of U, A union B is equal to B. Okay, so let's draw a picture. We start out with some set U, and we're supposed to find some unique A in the power set of U, so a subset of U, such that for every subset B of U, A union B equals B. Okay, so we have to specify an A, and then for every B in U that we are given, the union of this B with the A we've chosen has to be just B again. Okay. Now the only way that the union of B with something can be B is if that other set is itself a subset of B. Okay. But it doesn't just have to be a subset of that B, it has to be a subset of every possible subset B of U. Right? We have to choose the A before we're told what B is. Or a better way of saying it is that the single A has to work for every B. So we need to pick something which is a subset of every possible subset of U, and the only thing that satisfies that condition is the empty set. Okay, so it is in fact unique. Alright, so let's work that one out from the logical notation. Here's the goal. There exists a unique A in P of U, such that for all B in P of U, A union B equals B. And that's going to be broken into two separate goals. The existence and then the uniqueness. And let's take care of existence first. We have to decide what we think A should be, and our picture told us that we think A should be the empty set. So we will let A equal the empty set, and then we have to check that that A is in fact in the power set of U, and this remaining statement holds as well. And A being in the power set of U means that A is a subset of U. So that goal's all taken care of. The empty set is certainly a subset of any set U. And then for our other goal, well, we'll just let B be an arbitrary element of the power set of U. And we have to prove that A union B equals B. And so we know that B is a subset of U. And when we do A union B, we're just doing the empty set union B, which is certainly equal to B. So that takes care of existence. And then for uniqueness, here's our goal. To deal with these universal quantifiers on the beginning here, we will let S and T be arbitrary elements of the power set of U. And then we have a conditional statement here. This quantifier here is inside of the big antecedent of the conditional. Okay. And so we will do direct proof, move that antecedent over as a given. And I have added this in here because, well, let's think about what I'm going to need to do with my givens. I'm trying to prove that S equals T, and I have a universal statement here regarding B. And so I kind of needed a universal instantiation to get something here that I can work with, because I want the B to go away. And I want to get something about S and T. So, well, if I let B be the empty set, then I'm going to have just S on the left-hand side of this equation, because S union the empty set will be S, and similarly with this one. Okay, so it seems like a good idea to let B be the empty set, and we can do that because B can be anything in the power set of U, and empty set is certainly in the power set of U. So I will add that true statement in there as a given. Then go ahead and do my universal instantiation to replace the B here by the empty set. And so we get that S union empty set equals empty set from this one, and from this statement, the same thing for T. And then we just need to simplify those. S union the empty set is S, right? And T union the empty set is T. So we have S equals the empty set and T equals the empty set, and therefore we have our goal, S equals T. So let's write down the proof. We started out with there exists a unique statement, and broke that up into an existence goal and a uniqueness goal. And started off with existence. We had to decide what A was going to be, and we settled on the empty set. And our new goals were right here. And go ahead and write up what we have so far. So we should say first we're going to prove existence. And for that, we'll let A equal the empty set. And right away we see that, well, either the empty set is an element of power set of U, or if you prefer, it's a subset of U. I'll probably go ahead and just mention that one. So say A is the empty set and element of power set of U. Okay, and then our other goal is right here, and to deal with this universal quantifier, we will let B be an arbitrary element of power set of U, which just means this. And together with A being the empty set, that gives us that A union B is B, right? That's just the empty set union B is B. So we said let B be an arbitrary element of power set of U, and then A union B equals, well, A is the empty set, so that's the empty set union B, and that is B. Alright, so that is the existence proof. And then we went for uniqueness. And so first of all, we had to take S and T to be arbitrary elements of power set of U, leaving us with this conditional statement as a goal. And then this huge antecedent here became a given, leaving us with a goal of S equals T. Let's write that down. So next, we prove uniqueness, and we let S and T be arbitrary elements of the power set of U, such that for all B in the power set of U, these two equations hold, right? We have S union B is equal to B, and T union B is equal to B as well. And our goal is to show that S is equal to T. Good. So how did we get there? We wanted to do a universal instantiation here, and so we decided to use the fact that empty set is an element of the power set of anything. And so sort of applying this statement in the case where B equals the empty set, we arrived right here, and then just simplifying the left-hand side of each equation we got here. And those two equations together gave us that S equals T, which is our goal. So I'll just say we have in universal instantiation, I can say in particular that S union the empty set is equal to the empty set, and T union the empty set equals the empty set. And then just combining these inequalities, we get that S equals the empty set from the first one, and then simplifying the second one, flipping around, we get that that is equal to T. And so from beginning to end of the chain there, we see that S is equals T as we wanted to show. So we're finished.